This video is an introduction to a concept called momentum. Isaac Newton described momentum as the quantity of motion. And it is often confused with force. Students often think that an object moving very quickly is somehow a force. And they'll see a speed and they'll say, well, of course it has force, because if it crashes into something, it can exert a force. But as we'll see, the two are related, but they're not the same thing. Velocity is not force, or else we would have called it force. It has a different name because it's a slightly different thing. So we'll see that hopefully more clearly once we understand what momentum actually is. Momentum is the product of two things: an object's mass and its velocity. Objects with very large mass have a lot of momentum, even if they're moving slowly. The engine of a train, even if it's moving at only 1 or 2 meters per second, is still going to do a lot of damage if it collides with you. You'll have a hard time stopping that train because of the large mass. But even small things like a tiny bullet can also do a lot of damage if it's moving very quickly. So it's possible for a train and a bullet to have the same amount of momentum. One gets momentum by being very massive and slow moving. The other would get its momentum from being very small or less massive and moving very quickly. So we write this very simply. We use a little p for momentum because m has been used for too many other things, I guess, like mass. And so we have mass times velocity. And we should remember that since velocity is a vector and has direction, when you multiply it by mass, you will get an answer that is also a vector. So momentum is a vector, and the direction of momentum is very important. Don't forget that. Okay? It has direction, one way or the other. Let's do a simple little question. Let's do a little example here. A train. And let's say this train has a mass of, well, you know what? We don't want big numbers in our example, so let's make it a toy train. And the toy train has a mass of 5 kilograms. A toy train is moving on a toy track at, let's say, 3 meters per second. What is the momentum of the train? What is the train's momentum? And we can do this as a plug and play type problem. We know that momentum is equal to mass times velocity. I'm not going to put in the little vector arrows every time because it just clutters up the board and wastes a little bit of time. But we all remember that momentum is a vector. So 5 kilograms multiplied by 3 meters per second, and you would end up with 15. And of course we need a unit, 15, and the unit is, if you look at here, we've got a kilogram, that's the mass, multiplied by 3, which is meters per second, this is velocity. So it's a kilogram times a meter per second. And that's precisely what we call it, a kilogram meter per second. You might recall that there's another unit, a unit of force. Force is m times a. And it's kilograms times meters per second squared. Very close, but not quite the same thing. In fact, we've given this guy a special name. We call him a Newton in honor of Isaac Newton. As far as I know, there is no special name given to the unit for momentum. Not yet, anyway. So maybe you could work on winning a Nobel Prize and using your last name as the unit for momentum in the future. But for now, it's just kilogram meters per second. All right. Now, let's think more about what we were talking about. How can momentum be related to force? Well, if you have a train that's crashing into something, anytime two things crash or collide, obviously their speeds change. They slow down or sometimes speed up if they were standing still in the first place, which means that the forces involved in a collision of two things have something to do with how the momentum is changing. And so what we're going to do now is we're going to talk about how we describe a change in momentum. Well, there's two ways you can change momentum. Well, two ways you can do it. One way is to change the mass of something. That's not easy to do. It's not easy to do. It's hard to imagine how you would change something's mass. But if you, for instance, thought about yourself riding in a hot air balloon, and in this balloon they carry bags of sand on the side so that they can change the mass of the balloon. If the balloon's at a constant speed and suddenly you drop one of the bags down below, well, that mass is gone. So you've changed the mass of the balloon, and consequently you would change the they would change the balloon's momentum. So you can change the mass of an object by adding or subtracting mass to it. More commonly, though, the way we change momentum, another way to change momentum, and in fact the more common way, is to change the velocity of the object. Change how quickly it's moving. And of course that is, we see that all the time. We're in the car, we slam on the brakes, we change the velocity of the car, which means we change the car's momentum. Now, because changing momentum is such an important concept, we actually give it its own name, right? It's called impulse. Impulse is what we give to the change in momentum. So we could write, impulse has a symbol, but it's not an I. I is used for a lot of other things too. It's a J. And I suppose maybe if you think that J and I both have dots, that might help you remember that J is impulse. And it is equal to the change in momentum, which could be thought of as P2 minus P1. Just like we did, you may recall, the change in velocity, V2 minus V1. Change in displacement, D2 minus D1. The change in anything is the difference between the initial and final situations. Now, we never gave V2 minus V1 a special name, did we, when we learned about it? Neither did we give this a name. We just called it the change in velocity. But the change in momentum does get a name. It gets its own special name, and it's called impulse. So let's think about how we might calculate the impulse of something. Well, let's draw a line, and let's talk about a car. An 800 kilogram car is moving at 20 meters per second. If it slows to 15 meters per second, calculate the impulse on the car. Impulse. All right. So impulse is equal to the change in momentum, which is momentum 2 take away momentum 1. Now remember that momentum is mass times velocity. So momentum 2 would be the mass times velocity 2, and momentum 1 mass times velocity 1. And if you wanted to, you could do a little algebra here to make your math simpler. Or you could just plug in the numbers as it was before. It really doesn't matter. The mass of the car was 800 kilograms. And the second velocity of the car, remember, it slowed down to 15. And that's the second velocity. And the initial velocity, V1, was 20. So what we have down here then is 15 take away 20. And we get 800 times 5. actually, sorry, times -5, and that's very important, right? Because remember, impulse is a change in momentum, and momentum is a vector. So impulse is also a vector. What would this be? 4,000. And because it's a change in two different impulses, its unit would still be the kilogram meters per second for impulse. And it's a negative number. The negative number indicates that indicates, they're terrible spelling. The negative indicates a loss of momentum. The car slowed down. Its speed got lower, which means that it lost momentum. So the negative signs mean either a loss or a gain when we're talking about impulse. So negative for loss, a positive would be a gain, that's what I should have said. All right, so that's what we have for impulse. Now we have one more thing to think about. Let's think about the force that we all were thinking about before. How is the force related to this momentum and this change in impulse? Well, in order to change the momentum of something, you have to change its velocity. And so, if you recall Newton's law of inertia says that things don't want to change their velocity. They want to keep the same velocity and keep on doing whatever they were doing before. And in order to change the velocity, of course, you need an unbalanced force. So an unbalanced force will change velocity, which means it will also change your momentum. But it'll take a little bit of time for that to happen. You'll have to push on something for a certain amount of time in order for it to happen. And so you see what we have here is that force can be thought of as the change in momentum compared to the time that it takes to make that change. So force is what we would call the rate of change in momentum. The rate of change of momentum, I guess is a better way to say it. We've already learned about some other rates of change. If you recall, we learned that velocity is the rate of change of displacement. It's d2 minus d1 over t. And we learned that acceleration is the rate of change of velocity, v2 minus v1 over t. Notice how these equations look very, very similar to what we have up here for force. So we have now expressed force as a rate of change in momentum. And so what we will do is just kind of show you a couple different ways of writing that. So let me write what we just had up above, the rate of change of momentum, which could be written as this also. Same thing. But remember, we have a special name for P2 minus P1. That is the impulse. So I could also write force is impulse divided by time. And of course, if I multiply both of these by t, both sides of this, I can get impulse equals force times time. That's usually the way it's written in textbooks. Impulse equals force times time. And force is the rate of change of momentum. All right, it's time to do an example where we use all three things. So, let's say we have a baseball. And if I recall, the mass of a baseball is somewhere around 0.15 kilograms. For some reason, I remember looking that up not too long ago. And the baseball is moving because it's been thrown by the pitcher. Big league pitcher can throw a ball somewhere around 100 kilometers an hour. And so we're going to say it's moving at 30 meters per second, which is pretty much that. Pretty close. This would be a real fastball. When it is caught by the catcher's glove. the back catcher. So it was a swing and a miss, and the ball is now in the back catcher's glove, strike one. If it took 0 point, now it's not going to take very long to come to a stop in the glove. If you ever watch a ball get hit by, or get caught by a glove, it's moving very fast, and then in an instant almost, it goes from 30 meters per second to 0. So we're going to make this a very small number so it can stay realistic. We're going to say 0.05 seconds. Very, very quickly to come to a stop. In the glove. We're going to calculate, actually we're going to use this as a review and calculate a whole bunch of things, all the things that we've talked about. First, A, we're going to calculate the initial momentum of the ball. Initial momentum of the ball. Well, momentum is equal to mass times velocity. Vectors, remember. And I said the mass of the ball was 0.15, and initially the ball is moving at 30 meters per second, and so that comes out to 4.5 kilogram meters per second. That is the initial momentum of the ball. All right. Part B is going to be calculate the impulse of the ball as it comes to a stop in the glove. So impulse is equal to the change in momentum, which would be the final or second momentum take away the initial or first momentum. Well, the second momentum would be the mass times the second velocity, and the initial momentum is the mass times the first velocity. And so the impulse would be equal to 0.15 for the mass, and the second velocity in the glove is stopped, it's 0. Take away 0.15 for the mass again, and then 30 meters per second. Notice how we get a number that looks very familiar. And it's the same unit because it is a change of momentums. And we say, oh, isn't impulse the same then as momentum? Well, no, it's not. This number is 4.5, represents the initial momentum. This number represents how much the momentum has changed. And this little negative sign here is the difference, which means that momentum was lost by the ball, a loss of momentum. Now it happens that it's the same number because if you look here, this turned out to be 0. So if you go from 30 to 0, well, obviously your change is 30. But if you go from 30 times 0.15 to 0, your change is 4.5. So it's a slightly different concept, slightly different. This is telling us how much it has changed by. You could imagine if this was not a 0, then the number we got right here would be a completely different number, wouldn't it? It just so happened here that it worked out the same. All right, that's the momentum. Now, one more thing. Let's try to figure out the force. So this would be part C. Calculate the force stopping the ball. The force of the glove on the ball. Maybe that's a better way to say it. The force of the glove stopping the ball. Well, we have learned that force can be expressed as the change in momentum divided by the time, which is equal to P2 minus P1 over T, which is equal to the impulse divided by the time. And so conveniently, the force that I have here is equal to, I have the impulse already. In part B, it's negative 4.5. And so if I put negative 4.5, and I divide that by the time, which I said was, if we go back, 0.005, I believe, is the time that we picked for this very, very, very quick change. Here it is, 0.0005. No, sorry, too many zeros, 2 zeros and a 5. And we're going to multiply that, or sorry, divide that. And 4.5, you can do that in your head. 4.5, and you're dividing by 0.005, so it looks like it'd be about 900, right? 900 newtons. Because remember, you're taking a kilogram meter per second, that's the impulse, and you're dividing it by seconds. And so there's a seconds and here's a seconds, which turns into meters per second squared, and a kilogram per meter per second squared is a newton. So we're back to force. Right. Now, incidentally, to show you something, what we could also do is not abandon Isaac Newton altogether. We had a V1 of 30. We had a V2 of stopped, or 0. And we had a time of 0.005. Now I got to go check that number, because now I'm thinking that we got the time wrong. Let me just double check. That's the number we picked for time. Ah, see what I did? I put another 0 in there by mistake. But that's okay. We'll just do that, and if you're taking notes, make that little correction, then it'll all work out fine, because this is the first time we've used that number. So rather than erase everything we've done, see right here how I made that mistake. So 900 is still the correct answer. And we'll use the same number here so we don't get a different answer. But look what happens if we try to calculate the acceleration. That's what I was really getting at anyway. Negative 30 divided by 0.005. Well, that's a big number, isn't it? That's going to be 6,000 That equals negative 6,000 meters per second squared. That's the acceleration of the ball as it hits the glove. Of course it's going to be huge, because it goes from a very fast speed to nothing in a very short time. Now, what about good old Isaac Newton's second law, which says that force is ma? Well, let's see what happens if we put this in here and we multiply it by this negative 6,000. Well, what we end up getting is the exact same number, 900. Now this is a negative 900, and I guess up here we should have had a negative 900 on here too, right? And sometimes you see this is what happens. You get going and you forget that these little negative signs are kind of important. So that was a bad habit of mine, to forget that. What does that negative sign mean? Well, you'd say, well, it's still 900 newtons. It's still the correct answer. It is. But that negative sign is telling us that the force is applied in a direction opposite to the way the ball was moving originally. And that's kind of important if we really want to understand what's happening. And here we get a negative 900 newtons because, again, the force is in the opposite direction. So we can still use Newton's second law, but of course we didn't know what the acceleration was. We had to do this little bit of extra work here to figure it out. And if we use our new idea that force is the rate of change of momentum, we can cut ourselves down by one step and get the correct answer. So we haven't really learned something new. We've just learned a different way to express force, a different way to look at it. But it's really the same idea. And it's all related to, guess what? Changing velocities. Because in acceleration, velocities change. And when you change momentums, you are also changing velocities. So really, the key is changing velocity in all of these things. So now you have some new terms: momentum, impulse, and you can express force as the rate of change in momentum. And in the next video, we'll do some questions where we actually have several objects colliding with each other, and we'll do some fun collisions and see how momentum can be thought of in terms of things colliding.